Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 8th, 2025, about 3 days ago. This paper introduces a new mixture of components attention system that makes compositional three-dimensional generation scale efficiently to as many as 32 parts per object, while beating previous methods on both object and scene quality. The paper is titled MoCA, Mixture of Components Attention for Scalable Compositional 3D Generation. And as we will see later, the way this model focuses attention on only the most relevant parts has really exciting implications for complex three-dimensional asset creation. Also, the authors shared a GitHub repo for MoCA, but right now it is mostly a placeholder. Listeners will find a brief project description, a TODO noting plans to release the technical report, code, and models, plus some asset files, but the actual implementation has not been published yet. Alright. The introduction just laid out the motivation for compositional three-dimensional assets. Figure 1 now shows what that looks like in practice, with a full scene of colorful three-dimensional objects composed from many separate parts. The left side highlights individual gadgets and vehicles that are built from clearly segmented components. The center region focuses on character-like creatures, where limbs, armor, and wings are all distinct pieces. The right side illustrates richer scenes such as houses and furniture layouts, which demonstrate instance-level composition with complex arrangements. So while Figure 1 showed the kinds of multi-part assets MoCA targets, Figure 2 explains how the system actually generates them. The left side takes an input image, encodes it, and turns each object component into noisy latent vectors plus learnable query tokens. The central block is the compositional diffusion transformer, which alternates local attention with mixture of components attention to let parts talk efficiently. The right side decodes the cleaned latents back into separate three-dimensional components that assemble into the final scene or object. Well, Figure 3 zooms into the global block and shows how mixture of components attention actually routes information between parts. The three strips along the bottom depict different components, with full vecset tokens on the left of each strip and compressed tokens plus the anchor on the right. The central router box reads the anchor tokens and assigns importance scores, deciding which components send full details and which send only compressed context. The top row of QK versus attention blocks then performs standard attention over this mixed set of routed tokens, with importance scores gating how strongly each component influences the highlighted component. So, while Figure 3 unpacked how mixture of components attention routes information, Table 1 shows what that buys in practice for part-composed objects. The table compares 4 methods on 2 datasets using self-intersection over union, chamfer distance, and F-score at coarse and fine thresholds. Lower self-intersection over union and chamfer distance mean cleaner geometry and less part overlap, while higher F-score means better shape alignment. Across both datasets, the MoCA row consistently has the best combination of lowest errors and highest F-scores, indicating sharper parts and more accurate overall shapes. Alright, while Table 1 focused on single objects, Table 2 reports instance-composed scene quality on the three-dimensional front dataset. The columns list self-intersection over union, scene-level chamfer distance and F-score, and object-level chamfer distance and F-score. Lower self-intersection over union and chamfer distance mean fewer overlaps and closer geometry, while higher F-score means better reconstruction. The MoCA row achieves the lowest self-intersection over union and scene chamfer distance and the highest scene F-score, and it also leads on object-level metrics where they are available, beating both MIDI and PartCrafter. So after the quality metrics favored MoCA, Table 4 shifts to speed and breaks down runtime per forward pass. The left columns list part counts and separate local attention, routing, and global attention costs. The key pattern is that MoCA makes global attention much faster than PartCrafter, especially at 32 parts. But the routing step itself is expensive, so the total runtime only modestly improves at large scale. MoCA shows that mixture of components attention can scale compositional three-dimensional generation to dozens of parts while actually improving geometry quality and scene realism. Routing to important components and compressing the rest looks like a general recipe for making structured, part-aware models more efficient. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.